Good morning. My name is Riangwede Magodi of student number 57113920. Today I will be presenting to you about alternating energy design of the hospital in Venda Chilidzini Hospital. It is important for you to listen to me as I'll be presenting the alternating energy about the rural area hospital, whereby I will be highlighting the most important parts of my design. Abstract. Chilidzini Hospital in Limpopo faces frequent blackouts from load shedding and an unstable grid, threatening vital services like surgeries and vaccines storage. A solar PV system with battery storage is proposed to provide reliable, sustainable power, reducing reliance on ESCOM and supporting continuous healthcare operation. My introduction is as follows. South Africa faces ongoing electricity shortages, severely affecting hospitals like Chilidzini in Limpopo Bembe district. Frequent power cuts disrupt critical services, highlighting the need for renewable energy integration. With Limpopo's high solar potential of over 5.5 kilowatts hour per meter squared per day, a solar PV and battery storage system is proposed to ensure reliable, efficient, and independent power for hospital. These are my objectives. The project aims to design an alternating energy solution for Chilidzini Hospital to ensure continuous, efficient, independent power supply. These are my objectives. Number one, to develop SN's 10142 compliance solar PV systems with sufficient battery backup capacity. This is the standard, the one which you must comply with to maintain continuous hospital operations during grid outages. Objective 2, to calculate the hospital's maximum load demand and determine its daily energy requirements, ensuring the solar PV design meets both critical and non-critical loads profiles efficiently. So this is very important because now in this part, this is where you calculate the hospital's load which it can take. So that is why it is very important to have the proper calculation to make sure that the hospital maximum load demand is achieved. Literature review. Under this topic, it's where the studies show that the solar PV systems with batteries short storage are efficient, effective for hospitals facing power instability in sub-Saharan Africa. The UNFCCC and IRENA highlight solar PV as the most affordable renewable options, with the cost steadily declining. In South Africa, research links load shedding to healthcare disruptions, especially in Limpopo. Data from the World Bank Global Solar Atlas shows Limpopo's highs solar potential over 5.5 kilowatts meter squared per day, making PV systems ideal. For Chirizini hospitals, such as a system would ensure stable power, improve healthcare reliability, and support national renewable energy goals. In this slide, I will be highlighting the most important part of a theory on the low voltage installation, where the main goal of low voltage installation theory is to guarantee dependability and safety in unusual operating circumstances. Given that fault currents in low voltage systems can exceed several kiloamperes and result in serious harm, short circuit prevention is one of the most important features. According to the standards like SENS 10142-1 and IEC 10947-2, protective devices must quickly resolve issues in order to reduce mechanical and thermal strains. High rupturing capacity fuses and circuit breakers with magnetic trip units are examples of common equipment. To avoid complete hospital blackouts, device selective is crucial. This is the picture whereby you can see my protective device. This is the protective device, overload protection devices. So voltage drop directly affects system effectively and equipped performances, potential causing motor or device failure. IEC 60364 limits voltage drop to 3 to 5%, manageable through load balancing, shorter conductors, and proper cable selection. So it is important for you to select the proper cable selection, whereby the conductor, it must be properly be within 3 to 5% manageable for the load. This is just my diagrams which are showing the layout for the lighting layout, a small power layout, a design layout, and my there you can see my design, the SLT results. I'm going to show this slide is going to show the results, the calculation which I got on the voltage drops for nominal, which is 208 volts. Number one, exterior lights, which is 0.2223 stroke 208 multiplied by 100, which will give you the 0.111 percentage. So there will be reception and walk-away lights, warehouse, kitchen, doctor lights, ward lights, reception sockets, warehouse sockets, ward sockets, dedicated sockets, motor. With these dedicated sockets, it is very important because the dedicated sockets, it simple means the PV systems, it doesn't have to be connected to the wall sockets for the wards, receptions, warehouse, kitchen. No, In this one where you have dedicated sockets, it helps so that if there's a problem with the sockets, it won't trip everything, so the hospital can still operate in a normal way, because these dedicated sockets are only to minimize the load on the sockets for the hospitals. Calculations which are required for power. Exterior lights where there will be 230 watts. Reception walkaway lights where there will be 454 watts. Warehouse for the doctor and rooms and kitchen 163 watts. Wards lights will be 1347 watts. Reception walkway socket outlets will need 1390 watts. Warehouse and kitchen socket outlets will need 2300 watts. Wards normal socket outlets will need 1800 watts. Dedicated socket outlets will need 340 watts. Required power, it will be 8220 watts. So in kilowatts, it will give us 8.22 kilowatts. 8.22 kilowatts, this will be the power which is required for the whole hospital. This can ensure that there will be proper a backup on the load. These are the calculations for power ratings of components, where the inverter, I'm gonna take the previous 8.22 kilowatts, then that 8.22 kilowatts, it will be multiplied by 0.85, then it will give us 6.987 kilowatts inverter size. So this is the sufficient size which is needed for the hospital, because on the previous slides I was showing you the calculation for the whole hospital, the power which the hospital is taking from the ESCOM. So now for the backup power, which is PV systems solar, it will need at least 6.987 kilowatts inverter size. This will be sufficient for the whole hospital in case of load shedding. There is the calculation wattage of the solar panels. As you can see, the sum for the hours per day, where it will be 18,863 watts. Solar panels, or it can be 29. Yeah, 29 solar panels will be needed for the hospital, for the whole hospitals, for 250 watts. Here is my calculation for battery sizing. Here is the calculation where the battery sizing, we will need the capacity of 5729 Ah battery capacity for these systems, where we will need for 29 solar panels for 250 watts. The circuit breaking sizing, circuit breaker, the exterior lights, circuit breaker will be 5.91 amps. This sizing will multiply it by 125%, whereby we will get our 7.38 amps. Then when we do these calculations for the circuit breakers, we take the nearest circuit break standard for the circuit breaker. For example, where it's 7.38 amps, or then we take the nearest, which is 10 amps. Then as you can see, the reception size is 6.41. we will take 10 amps. On the warehouse for the doctor's room and kitchen, will also take 6.9 amps. The 6.9 amps, then it's gonna be converted to 10 amps. then we are going to have 10 amps for the lights. This is the calculation for the lights for reception, walk away outlets, socket outlets, where the nearest standards will be 20 amps because it's 15.6 amps. This is the standard which you must follow so that there won't be any tripping of the circuit breakers. We are avoiding the tripping of the circuit breakers by overloaded on the sockets. Warehouse and the kitchen socket outlets, the circuit current is 14 amps, then we're going to multiply by 1.25, then the nearest standard will be, it's 17.5 amps, the nearest standard will be breaker will be 20 amps. But this is to ensure that the safety on the breaker and the load, so that it must not be overloaded. It can be able to take the power amperage. The watts nominal socket outlets, it will be 15.6 to 25 amps. The nearest standard will be 20 amps. So there is the standard, the dedicated sockets outlets, also it's 18.125, where the nearest standard will be 20 amps. The nominal rating of a circuit breaker supplying the motor, it will be 13.5 amps. Then we are going to multiply it by 130%, which will give us 14.0. For this one is for the current, it is going to give us 14.04 amps. So this is very, very, very important to make sure that you've got the proper circuit breakers for the outrages, whereby you won't experience the power trips as to overload can cause that. It's gonna be very, very disappointing if you still have the overload while you are using solar panels, PV systems after load sheddings. So this is to ensure that the hospital won't encounter the problem. In conclusion, the study confirms that the solar energy is feasible and essential solution for reliable power in rural hospitals. Properly sized components ensure efficiency and resilience against load shedding, while reduced fossil fuel use supports South African sustainability goals and can be replicated in other rural facilities. So it is important for us to use the proper solar energy to avoid the outrages on the hospitals, the problems which the hospital can face. It is very, very important to use the proper sizes for the sockets to make sure that the proper running of the hospital continues, so that the hospital cannot face the blackouts during the load sheddings. This concludes my presentation. I thank you.